For this week's video, we're going to go over carboxylic acids and carboxylic acids derivatives. So as an introduction to carboxylic acids are compounds that contain the carboxyl group, which is a carbon led to an oxygen. So these compounds and their common derivatives make up the bulk of organic compounds, and their common derivatives include acid halides, which look like this, acid anhydrides, like this, esters, and amides. For the nomenclature of carboxylic acids, there's two systems used for naming, the common system and the IUPAC system. So we'll do naming, common, and IUPAC. So the common names for carboxylic acids are derived from Latin or Greek words that indicate the naturally occurring sources, and there's formic acid, there's acetic acid, there's butyric acid, and there's stearic acid. And we see this group 16 times. And for the IUPAC naming system, what you're going to do is you're still going to follow the rule of picking the longest continuous chain of carbon atoms that contains the carboxyl group, and the parent name for that compound comes from the alkane name for that number of carbon atoms. So picking the longest carbon chain. The second thing you're going to do is you're going to change the E ending to oic acid. And the third thing you're going to do is you're going to locate any substituents and labeling their placement, numbering away from the carboxyl group. So locate substituents. So you're going to apply these rules, and we're just going to do an example. So that's CH2. So your longest continuous chain, this is going to be 1, 2, 3, 4, 5. So we're going to get the name pentanoic acid. There's a methyl group right here. So we know that's going to be 4-methyl ethyl 2-ethyl pentanoic acid. And that's how you can go about it. For determining the acidity of carboxylic acids, the carboxylic acids show a Ka value that's going to be between 10 to the negative 4th to 10 to the negative 5th, and readily reacts with ordinary aqueous bases that can be sodium hydroxide, sodium bicarbonate. The acidity is typically due to two factors. First, the oxygen atom of the carboxyl group that's bonded to the hydrogen atom has a partial positive charge. So if we were to write this out, this is a partial negative and a partial positive. So strong nucleophiles are going to attack right there because it's a partial positive and a negative charge. The second is the anion that results from the removal of a hydrogen attached to the carboxyl oxygen is resonance stabilized. So that would be something like this. It's gonna move. And that's resonance stabilized. So substituting electron withdrawing groups, such as halogens on the chain of the R group, increases the acidity, and that's going to affect the strongest alpha substituent and decreases as the electron withdrawing group is moved further down the train. So let's go ahead and move on to some reactions of carboxylic acids. So carboxylic acids undergo reactions to produce derivatives of an acid. The most common derivatives that are formed are esters, acid halides, acid, sorry, let me rewrite this, esters, acid halides, acid anhydride, and amides. So esters are commonly formed by a reaction with carboxylic acid with alcohols. So I'm going to say with alcohol. They generally have a structure of this. We'll consider this R prime. The simplest method for preparing this an ester is the Fischer method, in which an alcohol and an acid are reacted in an acidic medium, and the reaction creates an equilibrium condition. The Fischer esterification proceeds via a carbocation mechanism, and so we can draw an example of one of those. So the carboxyl carbon in the carboxylic acid is going to get protonated. So we're going to see that right there. It's going to come up, and that's going to be in equilibrium with this. So you're going to see an alcohol molecule that is added. So we're going to have a reagent such as this. You're going to see this oxygen is going to attack right there. And what we're going to see is this product, or intermediate. And then a proton is going to be lost from the oxon ion. And so what we're going to see is that lone pair of electrons on that oxygen. And then a proton is going to get picked up. So this is supposed to be H plus. This proton is going to get picked up, and this is going to leave, and that double bond is going to form. And so what we're going to see is this. And then this hydrogen is going to get picked up by something, probably OH. That bond is going to break and it's going to go to the oxygen. And that is going to be our product. And this is a non-reversible ester formation. And we're going to do an amide preparation by reacting an acid halide with ammonia. So let's go for amides. And I think those are the more difficult. So esters and amides. And those are the two that I tend to need to work on. Or that I suppose I feel the most comfortable with. And so this is the product that we're going to see when an amide is prepared. And we're going to see an N-substituted amide prepared by reacting an acid halide with a primary amine. And so that is going to look like this. And another byproduct is going to be NH4Cl. And then we're going to see an NN disubstituted amine prepared by reacting with the secondary amine. So we're just going to take this down. And you can already see a pattern forming, which is going to produce, which was going to go in under, is going to undergo a reaction with ammonia and an ester to prepare a primary amide. And I think the last thing I'd add is the mechanism for an amide formation proceeds via attacking by the ammonium molecule, which acts as a nucleophile on the carboxyl carbon of the acid chloride or the ester. And we're just gonna move kind of straight on to the reduction of carboxylic acids. Which is going to give you carboxylic acid derivatives. So carboxylic acids, acid halides, esters, and amides are easily reduced by strong reducing agents. And examples of those strong reducing agents are going to be lithium aluminum hydride, and the carboxylic acids, acid halides, and esters are reduced by alcohols also, while amide derivatives is reduced to an amine. And so amides. So during the reduction of carboxylic acid derivatives, most reduction of carboxylic acids lead to the formation of primary alcohols. These reductions are normally carried out using a strong reducing agent, lithium aluminum hydride, and there's plenty of examples of this. You can also use diborane, which we haven't talked about a lot in class, to reduce the carboxylic acid to alcohol. So you could have something like just plain acetic acid, B2H6, ether, and you're going to use extra proton. So HCl plus and that is going to create or produce ethanol. During the reduction of esters, esters are normally reduced by a reaction with lithium aluminum hydride. So you could have something like propyl ethanate. Lithium aluminum hydride, ether, and H3O+. And that's going to create an ethanol and a propanol. For the reduction of acid halides, what you're going to see is acid halides are reduced by, guessed it, lithium aluminum hydride to primary alkyl or primary alcohol. So you can have benzoyl chloride, and that's going to produce benzyl alcohol. Just like that. For the reduction of amides, like other carboxylic acid derivatives, amides can be reduced by lithium aluminum hydride, and the product of that reduction is an amine. So you could have propanamide, if you can't tell already, lithium aluminum hydride is very, very important. It's useful, it's not very toxic, and it's pretty cheap, so it's easily accessible. Reactions of carboxylic acid derivatives. Carboxylic acid derivatives are very active. The following kind of things we'll go over detail how carboxylic acid derivatives can be converted. Some of those reactions of like acid halides for acid halide or acyl halides, they're super reactive, so they're easily converted to esters, anhydrides, amides, and substitute amides, carboxylic acids. And we'll go over a couple of those reactions where X is going to represent the halide. So let's just go over an acid halide converted to an ester. We'll just do an acid catalyzed reaction with an alcohol to an ester, and you're going to see this kind of similar behavior, H plus and heat. It's going to be carbon. That's your ester. And this is going to be a pretty standard. If it goes to an anhydride, your product is just going to be, if it goes to an amine, you're going to be looking at this. With an N substituted amine, you're going to look at something just like this. For an acid, it's just going to be an OH group attached. And you can kind of see where we're going from there. But so for the reactivity of carboxylic acid derivatives, the conversion of one type of derivative into another occurs via nucleophilic attack on substitution reactions. In these reactions, any of the factors that we've previously learned about are going to be influential, but they're going to make that carbonyl group more easily attacked by a nucleophile, and that's going to have a favored reaction. And the order of reactivity is acid halides, anhydrides, um, esters, and amines. Oopsies. Forgot if I was writing the structure or writing the word. Over here is going to be the most reactive and the least reactive. I hope that helped a little bit, but yeah.